Welcome to this intensive deep dive into risk management and process safety. We are really turning the intensity all the way up today.
Yeah, we're setting a high-energy, really fast-paced bootcamp vibe here.
Exactly. This session is specifically engineered for you, the safety professional out there, conquering the CHST, ASP, and CSP exams.
And we have synthesized a massive stack of sources for this. Transcripts, advanced study guides, exam prep materials.
And we're going to extract the absolute most critical, high-yield technical knowledge you need to pass.
Right, because the overarching mission today is bridging that massive gulf between abstract, textbook safety theory and critical real-world application.
Because we are analyzing the foundational systems that keep workers alive in the most catastrophic, high-energy scenarios imaginable.
I mean, the board exams do not simply test your ability to define a term. They test your ability to evaluate a cascading failure and implement the correct systemic control under extreme pressure.
So by the time we wrap up, you are going to possess a masterful command of the hierarchy of controls, including the nuances that the exam writers use to trick industry veterans.
You're going to crack the complex deductive logic of fault tree analysis.
We are going to train you to identify and dodge the incredibly sneaky mathematical red herrings hidden in the exam questions.
And you're going to dominate the structural intricacies of the incident command system.
This is not about memorizing flashcards. When a high-pressure chemical line ruptures or a worker is suspended unconscious in a harness, the cognitive frameworks we outlined today dictate whether that situation ends in a rescue or a recovery.
Because knowledge in this field is only valuable when it is rigorously understood and flawlessly applied.
Right.
Understanding the mathematical variables of a ventilation formula is, it's useless if you don't recognize the real-world consequence of a mismatched unit of measurement.
The exams are designed to simulate that field-level pressure, forcing you to synthesize dense information and prioritize your actions immediately.
Absolutely.
So grab your mental notepad, because we are dropping right into the core blueprint of risk management, the hierarchy of controls.
Industry veterans treat this like a sacred text.
And for good reason. It forces a systematic prioritization of the most robust, fail-safe solutions over the easiest or cheapest ones.
But let's look at this through the lens of a CSP candidate.
Yeah, the exams won't just ask you to list the hierarchy. They will present a complex scenario and ask for the most effective control according to the hierarchy.
The top of the hierarchy, the undisputed gold standard, is elimination. You physically remove the hazard from the workplace entirely.
Period.
Right. If a manufacturing process requires a highly volatile chemical that frequently causes secondary fires, you re-engineer the end product so that the process is no longer required. The hazard is gone.
But in the field, true elimination is incredibly rare because it usually requires changing the business model.
Which forces us down to the second-tier substitution.
We swap the dangerous element for a less hazardous one.
You take out the highly toxic volatile solvent and replace it with a citrus-based water-soluble cleaner.
Theoretical substitution sounds perfect, but the exams often test your understanding of its limitations.
Yeah, the real-world friction of substitution is that the new, safer chemical often doesn't perform as efficiently as the toxic one.
Workers complain the new solvent takes twice as long to clean a machine part, which impacts production quotas.
Exactly. But from a purely risk management perspective, substitution drastically reduces the severity of an exposure incident, even if probability of use increases.
When we can't substitute, we hit the physical barrier, engineering controls.
We alter the work environment or the equipment itself.
We install local exhaust ventilation to capture silica dust at the source.
We interlock a machine guard so the stamping press physically cannot cycle if the door is open.
We mandate pneumatic lift assist devices on the assembly line so human spines aren't absorbing the kinetic force of a heavy load.
Engineering controls are favored heavily on the exams because they do not rely on human compliance.
The interlocked guard does not care if the operator is fatigued, distracted, or cutting corners.
It simply prevents the kinetic energy from reaching the biological tissue.
That brings us to the friction point. The textbook dictates that administrative controls, the fourth tier, are technically superior to PPE.
But let's be real.
Relying on a written standard operating procedure, a warning line, or a training sign-in sheet feels inherently weaker than strapping a literal hard hat on a worker's head.
So why did the certification boards insist administrative controls rank higher?
You have to view it sequentially along the timeline of an incident.
Personal protective equipment, the absolute bottom of the hierarchy, only mitigates the damage after the failure has already reached the worker.
The wrench is already falling. The toxic gas is already in the breathing zone.
An administrative control flawed as it is because it relies on fallible human behavior attempts to prevent the worker from standing under the falling wrench in the first place.
Work rotation limits the exposure time. A warning line keeps them out of the drop zone.
That distinction is vital for scenario questions.
Now, pay close attention to the fall protection hierarchy, because the specific sources for these exams highlight a nuanced sequence that catches seasoned construction pros off guard.
The dictated sequence is prevention, elimination, arrest, administrative, and finally, PPE.
That specific sequence intentionally separates prevention from elimination, which differs from standard general industry models.
In this context, prevention involves architectural foresight.
Designing a 42-inch parapet wall into the building's blueprints before the concrete is even poured, you prevent the hazard from ever materializing.
Elimination in this sequence refers to modifying an existing hazardous task.
Like lowering a light fixture to the ground level on a winch system so the maintenance worker doesn't need a ladder.
Then you move to fall. Arrest stopping a fall that is actively occurring.
Then administrative controls, like a dedicated safety monitor system for a roofing crew.
And finally, PPE, which in fall protection might mean the specific impact-absorbing hard hat you wear while suspended.
Memorize that specific 5-step sequence: prevention, elimination, arrest, administrative PPE.
Establishing the hierarchy naturally leads to how we evaluate the risks we are trying to control.
The sources draw a hard line between speculative risk and pure risk.
And the exams expect you to know the difference implicitly.
Speculative risk is the realm of the CEO and the investors. You launch a new product line, you risk losing millions of dollars, but the upside is potentially tripling the company's revenue.
There is a chance for financial gain.
Pure risk, which is our entire domain, offers absolutely zero upside.
There is no financial gain to be had. There's only the potential for catastrophic loss.
Operating a high-speed mechanical shear without a point-of-operation guard is a classic pure risk.
The company does not generate additional profit at the end of the shift simply because an amputation did not occur.
But if the amputation does occur, the resulting loss is massive.
Direct medical costs, workers' compensation premiums skyrocketing, federal OSHA citations, third-party liability lawsuits, and the devastating moral injury to the workforce.
To quantify and prioritize that pure risk, safety professionals rely on the risk matrix, which plots the probability of an event against the severity of the outcome.
Let's elevate this beyond a basic definition and look at a complex audit scenario.
You are auditing a massive food processing facility. You identify 2 critical violations. First, the daily sanitation crew is bypassing lockout-tagout procedures to clean the industrial meat grinders faster.
Second, you find a cylinder of oxygen and a cylinder of acetylene stored side by side in a remote maintenance shed, violating the 20-foot separation rule.
You must apply the matrix instantly. The lockout-tagout bypass is occurring every single day.
The probability of an incident is virtually guaranteed over a long enough timeline.
If a grinder actuates while a worker is clearing a jam, the severity is a guaranteed fatality or catastrophic amputation.
High probability multiplied by maximum severity places this squarely in the extreme immediate action zone of the matrix. You stop production immediately.
Meanwhile, the improperly stored gas cylinders are absolutely a federal violation and a severe hazard.
But without an active ignition source or mechanical impact in that remote shed, the probability of them spontaneously detonating is relatively low.
The severity is catastrophic, but the low probability mitigates the immediate risk score. You address the LTO crisis at 8:30 a.m. You address the cylinders at 8:30 a.m.
The certification exams heavily favor questions that force you to perform this exact triage. Always isolate the variable with the highest frequency combined with an irreversible consequence.
Beyond controlling risk, we have to talk about risk transfer. We see this constantly in large-scale construction, and it directly ties into OSHA's multi-employer worksite policy.
A massive multinational corporation wants to build a new headquarters. They do not hire the steel erectors and the electricians directly.
They hire a general contractor.
They execute a legal and financial risk transfer.
The general contractor assumes the operational liability.
The GC holds the specialized rep-up insurance policies. They manage the site logistics, and they bear the brunt of the liability if a subcontractor creates a hazard.
Under OSHA's multi-employer policy, the exams will test your knowledge of the 4 employer categories: creating, exposing, correcting, and controlling.
The GC is almost always the controlling employer.
Even if a GC's direct employees are nowhere near a hazard, if a subcontractor leaves an elevator shaft unguarded, The GC can be cited because they hold the ultimate authority to compel compliance on that site.
The financial realities of these liabilities bring us to the concept of return on investment, or ROI.
Safety professionals must speak the language of the chief financial officer to secure capital for engineering controls.
The Pareto principle, or the 80-20 rule, is highly applicable here. You will often find that 80% of your workers' compensation costs originate from just 20% of your hazard profile.
Frequently severe musculoskeletal disorders.
Exactly.
If you track the data and find that chronic lower back injuries are costing the company an average of $60,000 per claim in direct medical and indirect replacement costs, you have your leverage.
If you request $25,000 to install a specialized robotic vacuum hoist on the shipping line, the CFO might balk at the upfront cost.
But you demonstrate that preventing just one single back injury yields an immediate, massive, positive ROI.
The equipment pays for itself in less than a year.
That concept of cascading failures and systemic risk analysis bleeds perfectly into how we manage highly complex, volatile operations.
When the foundational math of safety doesn't work out and the containment fails, the consequences require an entirely different framework of management.
That transitions us directly into process safety management, or PSM, and the rigorous methodologies of fault tree analysis.
This is the heavy, industrial, highly regulated sector of our field.
The PSM standard wasn't drafted in a vacuum. It was written in blood following catastrophic industrial disasters.
The historical anchor for PSM is the 1984 Union Carbide disaster in Bhopal, India.
A massive release of methyl isocyanate, or MIC, gas blanketed the surrounding city.
Thousands of people died within hours, and hundreds of thousands suffered permanent respiratory and neurological damage.
The exams expect you to understand why Bhopal happened from a systemic perspective. MIC is incredibly reactive with water.
A routine pipe washing operation allowed water to bypass leaking valves and enter the MIC storage tank.
The resulting exothermic reaction caused the pressure to spike, blowing the relief valves.
The scrubber systems designed to neutralize the gas were offline for maintenance.
The flare tower designed to burn off the excess gas was disconnected.
It was a total failure of multiple redundant systems.
In direct response to Bhopal and similar incidents, the Clean Air Act amendments birthed the OSHA PSM standard.
It applies strictly to facilities that handle highly hazardous chemicals at or above specific threshold quantities.
For example, a facility processing 10,000 pounds of a flammable liquid or handling highly toxic inhalation hazards like anhydrous ammonia or chlorine.
When you have that much concentrated potential energy, a minor mechanical failure doesn't result in a single first aid case. It results in a neighborhood evacuation.
Of the 14 elements of PSM, 2 show up constantly on the exams: mechanical integrity and process hazard analysis, or PHA.
Let's look at mechanical integrity. It mandates that you cannot simply install a high-pressure chemical pump, turn it on, and run it to failure.
Running to failure is unacceptable under PSM.
Mechanical integrity requires a rigorous, heavily documented programmatic approach.
You must have established schedules for inspecting, testing, and replacing every critical valve, rupture disc, gasket, and piece of instrumentation based on recognized and generally accepted good engineering practices, or RAGACHAP.
The core of the standard, however, is the process hazard analysis.
The PHA is where safety engineers use structured methodologies to essentially predict the future and identify where the system will fail.
One of the most prominent tools is the HAZAWE, or Hazard Inoperability Study.
The HAZAWE is a brilliantly structured methodical examination of a planned or existing process.
It relies on the rigorous application of guide words to specific nodes in a piping and instrumentation diagram.
You take a parameter like flow or pressure and apply the guide words: more, less, none, reverse.
So the engineering team looks at a specific chemical feed line and asks, what are the immediate consequences if there is no flow?
What happens to the reactor temperature if the coolant flow goes in reverse?
By forcing the team to evaluate every possible deviation systematically, you uncover hidden catastrophic potentials that casual observation would miss.
If AAC's up is too rigid for a simpler process, teams might use a what-if analysis.
This is a less structured, more conversational brainstorming session where the team posits failure scenarios.
What if the primary intake filter clogs? What if the backup generator fails to start during a power loss?
You map the scenario to its ultimate consequence and ensure adequate safeguards exist.
We also see the fishbone diagram, or Ishikawa diagram, used extensively for root cause analysis.
You draw the spine of the fish ending out ahead, which represents the ultimate defect or failure.
The bones branching off the spine represent the major causal categories: machine, method, material, manpower, measurement, environment.
It visually organizes the contributing factors of a complex failure.
But the absolute crown jewel of risk analysis on the CST exam is fault tree analysis, or FTA.
This methodology originated in the aerospace and ballistic missile industries, where a single failure results in an unacceptable, catastrophic loss.
I'm going to hype this up because you must understand the logic gates of a fault tree. It's a highly analytical, deductive process. It works top-down.
The deductive nature is critical. You always start at the very top of the diagram with a single, defined, undesired top event.
Let's build a mental model. The top event is, worker is electrocuted by the automated stamping press. You place that in a rectangle at the top of your page.
Now, you use deductive logic to step downward. You ask what immediate preceding events must occur simultaneously for this worker to be electrocuted.
For electrocution to occur in this specific scenario, two things have to happen at the exact same time. First, there must be a catastrophic short circuit that energizes the metal casing of the machine.
Second, the secondary grounding wire connecting the machine to the earth must be severed or disconnected.
Precisely. Because both conditions must exist simultaneously for the top event to happen, you connect those two lower events to the top event using an A&D gate.
The visual symbol for an A&D gate looks like a flat-bottomed bullet.
But let's look at the short circuit event. Why did the casing become energized?
It could happen if the internal wiring insulation degrades over time, or if a forklift accidentally rams the control box and crushes the wires.
Because either of those events independently can cause the casing to energize, you connect them using an OR gate.
The visual symbol for an OR gate has a curved bottom, like a shield.
You continue this deductive branching identifying base events and connecting them with A&D or OR gates until you reach the absolute root causes, like a lack of forklift driver training or a skipped maintenance inspection.
The exams love to test your understanding of how these gates affect mathematical probability.
An A&D gate drastically reduces the probability of the top event because multiple independent failures must align perfectly.
An OR gate significantly increases the probability of the event because any single failure in the chain triggers the hazard.
You use this tree to identify cut sets, the unique combinations of component failures that lead to the top event, and you engineer solutions to break those sets.
Before we close out the PSM discussion, we must address management of change, or MOC.
In a highly energetic chemical process, you cannot simply upgrade a piece of equipment without a systemic review.
Let's say the maintenance manager realizes the pneumatic tools are sluggish, so they unilaterally purchase and install an industrial air compressor that delivers double the volume and pressure of the old unit.
They think they are improving efficiency.
In a PSM environment, they just created a bomb.
If you introduce a massive increase in pressure to a system without conducting an MOC, the existing piping infrastructure, the rubber seals, the valves, and the instrumentation, which were all rated for the previous lower pressure, will fail catastrophically.
An MOC requires a formal, documented engineering review to guarantee that a change in one isolated variable does not cause a cascading failure throughout the entire process.
When the MOC is ignored, when the fault tree probabilities align, and the containment fails, we enter the realm of disaster response.
That brings us to Section 3, Emergency Management and the Incident Command System.
When an anhydrous ammonia tank ruptures or a trench collapses on a crew, the response environment is pure chaos. You have local fire, police, EMS, state environmental agencies, and federal OSHA all converging on one site.
Without a standardized, pre-established management framework, that multi-agency response instantly devolves into a jurisdictional turf war.
The Incident Command System, a core component of the National Incident Management System, solves this by establishing a scalable, standardized hierarchy.
The foundational rule is unified command under a single incident commander, or IC. Every single resource on that site ultimately answers to the IC.
Let's break down the massive general staff structure that reports to the IC. We elevate this beyond basic definitions. These are complex logistical operations. First, you have the operations section.
The operations section is responsible for the tactical deployment of resources.
These are the specialized entry teams, actively turning the valves to stop the chemical leak, the shoring teams securing the collapsed trench, or the suppression crews fighting the fire. They execute the immediate tactical objectives.
Next is the planning section. While operations is handling the current operational period, planning is looking 12, 24, and 48 hours into the future.
They are analyzing meteorological data to predict where the toxic plume will drift tomorrow. They are drafting the incident action plan for the next shift and determining what specialized resources will be required as the incident evolves.
The procurement of those resources falls to the logistics section.
Logistics secures the operational infrastructure.
If operations needs 3 specialized hazardous materials vacuum trucks at 2:00 a.m., logistics procures them.
If 500 responders are deployed to a remote wildfire, logistics secures the base camps, the communication repeaters, the medical support, and the food supply chains.
Finally, the finance and administration section. Massive emergency responses burn through millions of dollars a day.
Finance tracks the personnel hours, executes the emergency procurement contracts, processes the heavy equipment rental agreements, and manages the inevitable workers' compensation claims from injured responders. Operations, planning, logistics, finance.
Managing all of those sections requires strict adherence to the concept of span of control. This is a critical exam topic.
In the extreme cognitive load of an emergency response, human beings can only effectively manage a limited number of communication channels.
If an operations section chief tries to directly radio instructions to 25 different tactical strike teams, critical information will be lost and responders will die.
The exams are explicitly clear on the acceptable mathematical range for span of control.
One supervisor can effectively manage between 3 and 7 direct reports.
If you have fewer than 3, you have a top-heavy management structure. If you have more than 7, you lose situational awareness and tactical control.
But the exam often asks for the optimal number.
The golden rule of span of control is 5.
5 direct reports allow for robust communication, strict accountability, and rapid tactical adjustments without overwhelming the supervisor's cognitive bandwidth.
Operating entirely separate from the general staff is the command staff. These are 3 specific, high-level advisory roles that report directly to the incident commander. First is the Public Information Officer, or PIO.
The PIO controls the external narrative.
You cannot have exhausted tactical responders giving unauthorized, conflicting interviews to local news crews.
The PIO gathers verified intelligence from the IC and disseminates accurate, standardized information to the media and the public.
Second is the Liaison Officer. On a massive hazardous materials response, you will have representatives from the EPA, the Coast Guard, State Emergency Management, and local municipalities all demanding information.
The liaison officer acts as the central point of contact for these assisting agencies, integrating them into the response structure so they don't bypass the chain of command and interrupt the IC.
And finally, the Safety Officer. We have to pause here because the authority vested in the Safety Officer within the ICS structure is absolutely unparalleled, and it is a massive focal point on the CSP exam.
The Safety Officer operates with unilateral authority regarding immediate life safety threats. Their sole operational objective is monitoring the incident for unsafe acts or conditions.
Let's paint the scenario. The Safety Officer is monitoring a deep trench rescue. They observe the soil walls beginning to fissure and slough off, indicating an imminent secondary collapse.
The textbook ICS chain of command dictates you radio your superior.
But in this singular instance, the Safety Officer does not have to radio the incident commander to request permission to halt operations.
They possess the explicit authority to bypass the entire chain of command and immediately, unilaterally, stop unsafe work.
They blow the air horn, evacuate the trench, and secure the lives of the responders instantly.
Only after the immediate threat is neutralized do they inform the IC of the action taken. Do not miss that nuance on a scenario question.
While we are discussing hazardous materials responses, we must address the HAZWOPER standard hazardous waste operations and emergency response.
The foundation of hazardous waste management relies on the RCRA concept of cradle to grave.
Cradle to grave establishes unbroken legal chain of custody.
If a chemical manufacturer generates a highly toxic waste byproduct, the cradle, they retain liability for that waste during transportation, during temporary storage, and all the way until it is definitively neutralized or placed in a permitted secure landfill, the grave.
A company cannot simply contract out a sketchy disposal firm and absolve themselves of the environmental and legal liability.
When that hazardous waste spills on a highway, HAZWOPER dictates strict site control using 3 concentric zones.
The exams will test your knowledge of how personnel move through these zones.
The absolute center of the spill, where contamination is at lethal concentrations, is the hot zone or exclusion zone.
Only highly trained technical responders wearing maximum chemical-resistant PPE operate here.
When those responders need to exit, they cannot simply walk to the command post.
They must transition through the warm zone, or the contamination reduction zone. This is where the physical decontamination corridor is established.
The physical realities of a decon corridor are arduous.
It typically involves a series of technical wash pools.
A responder, fully encapsulated in a chemical suit, steps into the first pool and is aggressively scrubbed with specific neutralizing solutions. They move to a secondary scrub pool and finally a rinse pool.
Only after they're certified clean by the decon team can they safely doff their PPE and cross the contamination control line.
They cross that line into the cold zone or support zone. This is the green area.
It's entirely free of contamination. The incident command post is located here, along with medical staging and the unequipped support personnel.
Hot, warm, cold. You only move outward after decontamination.
Operating in those zones requires specific tiers of HAZWOPER training. The entry-level tier is first responder awareness.
This applies to the highway maintenance worker who happens to discover the leaking tanker truck.
Their operational mandate is brutally simple. Recognize the hazard, evacuate to a safe distance, deny entry to others, and call for emergency response. They do not intervene.
They require sufficient training to recognize the hazard, but OSHA mandates no specific minimum hour requirement for awareness level.
The next tier is first responder operations, which requires a minimum of 8 hours of initial training.
Operations level personnel respond in a strictly defensive posture.
They stay outside the hot zone. Their tactical objectives are containment, deploying absorbent booms to keep the chemical from reaching a storm drain or diking the perimeter of the spill.
They do not attempt to stop the leak at the physical source.
That aggressive intervention is reserved for the hazardous materials technician. Tech-level responders require a minimum of 24 hours of specialized training.
They are the personnel donning the fully encapsulated suits, entering the hot zone, and physically applying patches, plugging valves, or securing the ruptured pressure vessel.
Finally, the general site worker. Once the emergency is over and the site transitions to a long-term environmental remediation project like excavating thousands of tons of contaminated soil over 6 months, those workers require 40 hours of formal classroom instruction plus 3 days of supervised field experience.
Equipping those responders requires a deep understanding of the EPA's 4 levels of PTE. Let's dissect them technically. Level A provides the absolute maximum protection for both the respiratory system and the skin.
You only authorize Level A when the chemical is highly toxic, completely unknown, or poses a severe skin absorption hazard.
The responder wears a positive pressure self-contained breathing apparatus, or SCBA, and they are entirely sealed inside a vapor-tight, fully encapsulated chemical suit.
The SCBA is worn inside the suit, protecting the equipment itself from corrosive degradation.
Level B drops the skin protection slightly while maintaining maximum respiratory protection.
You authorize Level B when the chemical presents a severe inhalation hazard, but is not a severe skin absorption or vapor hazard.
The responder still utilizes a positive pressure SCBA, but the chemical suit is splash-resistant, not fully vapor-tight. The SCBA cylinder is often worn on the outside of the suit.
The transition to Level C is where the exam sets a massive trap.
Level C replaces the supplied air SCBA with an air-purifying respirator, or APR. You are now breathing the ambient air, pulling it through a chemical filter cartridge.
You can only authorize Level C under extremely strict parameters. You must know the exact identity of the chemical. You must know its exact concentration.
You must guarantee the concentration is below the immediately dangerous to life or health threshold, the IDLH, and you must verify the ambient oxygen concentration is between 19.5% and 23.5%.
If any of those variables are unknown, Level C is illegal and lethal.
Level D is simply standard industrial work attire. Safety glasses, steel-toe boots, a hard hat, and perhaps a high-visibility vest. It offers zero specialized chemical or respiratory protection.
Understanding the physics of those respirators and the limits of those chemicals is crucial, but it's the mathematical application that truly separates candidates on the exams.
Which brings us to Section 4, Surviving the Math.
The exams are notorious for deploying mathematical red herrings, deliberate traps designed with too much information, practically begging you to calculate the wrong formula. I'm going to walk you through the TWA trap.
TWA, or time-weighted average, is the foundational metric of industrial hygiene. It calculates a worker's average exposure to an airborne contaminant over a standard work shift, accounting for the peaks and valleys of concentration.
The formula is concentration 1 multiplied by time 1 plus concentration 2 multiplied by time 2, all divided by the total hours.
Here is the trap, and it is devastatingly simple. The exam question will present a scenario where a specialized welder is exposed to a chemical for 4 hours on Monday, 4 hours on Tuesday, and then performs non-welding tasks for the rest of the 40-hour work week.
They will ask you to calculate the TWA. A significant percentage of candidates will multiply the concentrations by the times, get the total, and then divide by 40 hours because it's a weekly scenario.
If you divide by 40, you fail the question. The standard OSHA TWA is, by definition, an 8-hour daily calculation. You evaluate the specific shift in question.
Let's run the actual math to lock it in. During a single shift, a worker is exposed to a solvent at 50 parts per million for 4 hours. The ventilation kicks in, and the exposure drops to 30 parts per million for the remaining 4 hours of the shift. Calculate the TWA.
Step 1. 50 TPM multiplied by 4 hours equals 200.
Step 2. 30 ppm multiplied by 4 hours equals 120.
Step 3. Add the sums together. 200 plus 120 equals a total cumulative exposure of 320.
Step 4. Divide by the standard 8-hour shift. 320 divided by 8 gives you a time-weighted average of 40 parts per million.
It's simple arithmetic, but if you let the exam trick you into dividing by the 40-hour week, your calculation falls apart.
Now I want to tackle the second major math pitfall, the incident rate calculation trap.
The OSHA Total Recordable Incident Rate, or TRIR, is the standardized metric used to mathematically compare the safety performance of a 50-employee machine shop against a 5,000-employee automotive plant.
The formula is the number of recordable cases multiplied by 200,000, all divided by the total hours worked by all employees during the year.
The 200,000 constant is the great equalizer. It represents the baseline hours of 100 employees working exactly 40 hours a week for exactly 50 weeks a year. It converts tiny, confusing decimals into whole numbers we can easily track.
The trap lies in the definition of recordable cases. The exam question will present a massive table of data designed to overwhelm you.
I'll play the stressed candidate taking the test. I look at the screen and see this data set for a manufacturing plant. 14 medical treatment cases, 16 lost time cases, 50 first aid cases, 10 property damage incidents involving forklifts, and 5 minor auto fleet claims.
The total hours worked by the facility is 922,000. How do I sort through all of this to find the incident rate?
By recognizing that 80% of that data is a red herring. The TRIR formula strictly utilizes cases that meet the criteria for entry on the OSHA 300 log.
First aid cases, by definition, are not recordable. You discard the 50 first aid cases immediately. Property damage and auto claims do not involve biological injury to an employee. You discard them.
You strip away the noise.
Exactly. You only extract the 14 medical treatment cases and the 16 lost time cases. Add them together to get 30 total recordable cases.
Multiply 30 by the 200,000 constant, which gives you 6 milson.
Divide 6 milson by the 922,000 total hours worked. Your calculated incident rate is 6.5.
If you include the first aid cases, your math will match one of the incorrect multiple choice answers perfectly.
That is how they get you. They provide the exact answer to the wrong math equation. Moving to trap number 3, the Jack proof test trap.
I want to frame this with a real-world scenario because it highlights the friction between engineering standards and field mechanics.
Every large maintenance shop has that one ancient, heavy-duty hydraulic floor jack that the senior mechanic refuses to throw away. The manufacturer's label wore off in 1998. The safety manager demands to know its load capacity.
But the mechanic will likely tell you they've lifted 10,000-pound trucks with it for a decade, so it's a 10,000-pound jack.
The exams will offer multiple choice options suggesting you can establish capacity through a visual inspection by a competent person or by testing it with a load equal to 100% of its intended capacity. Both are incorrect and highly dangerous.
To legally establish the safe working load of an undocumented or repaired jack, the standard mandates a rigorous physical proof test at 125% of its intended capacity.
If the shop wants to rate that vintage jack for 10,000 pounds, they must systematically load it with 12,500 pounds in a controlled environment.
They must prove that the hydraulic seals hold the pressure without leaking, and the steel chassis does not deform under the excess stress.
Once it survives the 125% proof test, it can be officially tagged for a 10,000-pound working load. Look for the 125% multiplier on the exam.
Trap number 4 is the granddaddy of construction math, free fall versus total fall clearance. Candidates constantly conflate these two distinct measurements, and the exams exploit that confusion mercilessly.
We must isolate the physics. Free fall is strictly the distance a worker's body travels downward before the fall arrest system engages and begins to apply deceleration forces.
It is primarily determined by the length of the lanyard and the vertical placement of the anchor point relative to the harness D-ring.
Let's map it out precisely. You are wearing a full-body harness. The dorsal D-ring is situated between your shoulder blades, exactly 5 feet off the ground. You are utilizing a standard 6-foot shock-absorbing lanyard.
Let's calculate the free fall in scenario A. You secure the lanyard to an overhead anchor point that is exactly 2 feet above your D-ring.
Because the anchor is located 2 feet above the attachment point, 2 feet of your 6-foot lanyard is already extending upward.
When you step off the edge, you only have 4 feet of slack remaining before the system pulls taut. Your free fall distance is exactly 4 feet.
The trap is that stress test takers will try to add the 2 feet to the 6-foot lanyard, but if the anchor is above you, you subtract the distance.
Now, scenario B, the nightmare scenario. You tie the 6-foot lanyard off at the level of your feet.
This changes the geometry entirely. When you step off the edge, your D-ring must first fall the 5 feet, just to drop below the level of the anchor point on the floor. Only then does the 6-foot lanyard begin to extend.
You fall the initial 5 feet plus the full 6-foot length of the lanyard.
5 plus 6 equals an 11-foot free fall.
That is massive kinetic energy generation. OSHA generally restricts maximum free fall to 6 feet, making the foot-level tie-off non-compliant and highly lethal without specialized equipment.
So that is free fall. How does the exam differentiate that from total fall clearance?
Total fall clearance is the absolute vertical distance required beneath the walking working surface to guarantee the falling worker does not strike the lower level. It requires adding multiple variables.
You take your calculated free fall distance, you add the deceleration distance, the distance the shock absorber rips open to bleed off kinetic energy, which OSHA limits to a maximum of 42 inches or 3.5 feet.
You add the height of the worker from the D-ring to their boots, and you add a safety factor, typically 2 or 3 feet, to account for harness stretch and D-ring slide.
The exam trap is asking you to calculate free fall and offering an answer choice that incorrectly includes a 3.5-foot deceleration distance. Keep the formulas strictly separated in your mind.
Our final mathematical trap involves industrial ventilation. The fundamental formula for calculating airflow is Q equals V times A.
Flow equals velocity multiplied by the cross-sectional area of the ductwork.
The underlying math is elementary multiplication. The complexity and the trap lies entirely in the mismatched units of measurement provided in the scenario.
Exactly. I will explain the mechanics of this trap because it catches engineers in the field constantly. The velocity of the air moving through the system is almost universally provided in feet per minute.
However, the diameter of the physical sheet metal duct is almost always specified in inches.
The exam will state you have a 12-inch diameter circular duct and an air velocity of 300 feet per minute. The candidate rushing the math will use the number 12 to calculate the area, multiply it by 300, and arrive at a wildly incorrect flow rate.
You must harmonize the units before executing the formula.
Step 1 is geometric conversion. You have a 12-inch diameter duct. You have the diameter to find the radius, which is 6 inches.
Step 2 is the critical unit conversion. You must convert those 6 inches into feet. 6 divided by 12 equals 0.5 feet.
Now you can accurately calculate the cross-sectional area using pi times the radius squared. Pi multiplied by 0.5 feet squared, which is 0.25.
3.14 times 0.25 yields an area of exactly 0.785 square feet.
Only now do you apply the primary formula. Q equals V times A. Velocity, 300 feet per minute, multiplied by area, 0.785 square feet.
The resulting flow is 235.5 cubic feet per minute.
If you square the 6 inches, or worse, square the 12 inches without converting to feet, the exam writers have a multiple-choice answer waiting specifically for you. Always match your units.
Take a deep breath. We have survived the math gauntlet. We are pivoting to Section 5, Industrial Hygiene, the science of evaluating and controlling the invisible enemies.
The chemicals, vapors, and microscopic dusts that inflict chronic, devastating systemic damage to the human body.
Industrial hygiene is a vast discipline, but for the exams, you must first decipher the regulatory alphabet soup of exposure limits. You need to distinguish between the authoritative bodies, ACGIH, OSHA, and NIOSH. Let's begin with ACGIH and the TLVs.
The American Conference of Governmental Industrial Hygienists is not a government regulatory enforcement agency, despite the confusing name. They are a private scientific organization. Annually, they publish a compendium of TLVs, or threshold limit values.
TLVs represent the absolute cutting edge of peer-reviewed toxicological research. They indicate the airborne concentrations of substances under which it is believed that nearly all workers may be repeatedly exposed day after day without adverse health effects.
Crucially, TLVs are voluntary best practices, not federal laws. Because they adapt rapidly to new science, TLVs are frequently much lower and significantly more protective than legal limits.
The legal limits belong to OSHA. They promulgate the PADLs, or permissible exposure limits. If a facility exceeds a PEL, they are violating federal law and subject to severe citations.
The conflict between the two, which you must understand for practical application, is regulatory lag. The vast majority of OSHA PELs were adopted verbatim in 1971 from existing 1968 ACGIH standards, and due to complex legal and economic hurdles, they have rarely been updated.
Therefore, complying with a 50-year-old PL might keep you out of federal court, but it may not actually protect your workers from chronic disease based on modern science.
Then we have NEOSHA, the National Institute for Occupational Safety and Health. They are the federal research arm operating under the CDC. They conduct the studies and produce RELs, or recommended exposure limits. Like TLVs, they are highly protective recommendations, not enforceable law.
Beyond the 8-hour time-weighted average we calculated earlier, you must understand peak exposure limits.
The STEL, or short-term exposure limit, acknowledges that while an 8-hour average exposure might be acceptable, a massive, concentrated dose over a few minutes can be acutely toxic.
The STEL is an absolute 15-minute maximum exposure limit, but it comes with 3 strict caveats you must memorize. You cannot exceed the limit for more than 15 continuous minutes. You're only allowed to hit that cell concentration a maximum of 4 times during a single work shift.
And critically, there must be a minimum 60-minute gap of clean air between those 15-minute high-exposure events to allow the body to metabolize the toxin.
Finally, the ceiling limit, designated with a C. This is an instantaneous threshold that must never be exceeded during any part of the working exposure, not even for a fraction of a second.
It is typically reserved for highly reactive, immediate irritants such as chlorine gas or hydrogen chloride.
Let's transition into the ultimate industrial hygiene battleground, confined spaces. The exams require you to parse the exact legal definition of a confined space. It is a 3-part test, and the space must meet all 3 criteria simultaneously.
First, the space must be large enough and so configured that an employee can bodily enter and perform assigned work. If you can only stick your arm in, it's not a confined space.
Second, it must have limited or restricted means for entry or exit. Think of a 500,000-gallon chemical storage tank accessible only by a 24-inch manway at the top.
Third, the space is not designed for continuous human occupancy. It's a vessel for chemicals or grain, not a break room.
If a space meets all 3, it is a confined space. But the regulatory burden shifts massively when it becomes a permit-required confined space.
A space becomes permit-required if it contains any one of 4 amplifying hazards. It contains, or has the potential to contain, a hazardous atmosphere. It contains a material with the potential for engulfment, like a silo full of flowing grain.
It has an internal configuration that could trap or asphyxiate an entrant, like inwardly converging walls. Or it contains any other recognized serious safety or health hazards, such as exposed high-voltage wiring.
The atmospheric testing of these permit spaces is a hypercritical exam concept. When the entry supervisor arrives with the direct reading 4-gas monitor, there is a rigid, non-negotiable protocol for the testing sequence. What is the exact order, and what is the underlying physics dictating it?
You must evaluate the atmosphere in this precise order. Oxygen first, flammability second, and toxicity third. The reasoning lies in the electrochemical mechanics of the sensors.
The flammability sensor, specifically the catalytic bead LEL sensor, physically burns a tiny amount of the ambient gas across a heated wire to measure the explosive concentration.
Precisely. To support that internal combustion, the sensor requires an ambient oxygen concentration of at least 10 to 15%. If you insert the meter into a space where the oxygen has been completely displaced by methane gas, the LEL sensor cannot burn the methane.
The meter will digitally read 0% flammability, lying to you. If you authorize entry based on that false 0, the moment an entrant strikes a spark, the space detonates.
That is why you verify oxygen content first. You ensure the space can support life and support the sensors. You test flammability second because an explosion is instantly lethal to the entire team. You test toxicity third because toxic gases typically require time to inflict neurological damage. Oxygen, flammability, toxicity.
Executing a permit-required entry involves 3 strictly defined roles. the authorized entrant, the entry supervisor, and the attendant. The entrant is the personnel physically breaking the plane of the space to conduct the work.
The entry supervisor is the management representative who verifies all isolation and ventilation protocols are met, signs the legal permit, and holds ultimate responsibility for the operation.
Then we have the attendant, often called the hull watch. I'm going to aggressively emphasize this next point because it is a matter of life and death, and it is heavily tested. The attendant remains stationed immediately outside the portal. Their sole duty is to monitor the entrance, control unauthorized access, and initiate emergency protocols.
The exam will inevitably present a scenario. An entrant collapses inside a subterranean vault due to an unknown atmospheric hazard. The attendant is standing outside. What is the attendant's immediate action? The multiple choice options will tempt you with heroic answers like hold their breath and pull the entrant out.
The attendant never, under any circumstances, breaks the plane of the confined space to attempt to rescue.
Never. The historical statistics are a tragedy. Over 60% of all confined space fatalities are would-be rescuers, attendants, or supervisors who react on pure human instinct, rush into the space to save a collapsed coworker, and are instantly overcome by the exact same invisible asphyxiant.
The attendant is strictly limited to operating external, non-entry mechanical retrieval lines connected to the entrance harness, or immediately radioing for a highly specialized SCBA-equipped technical rescue team. The moment the attendant enters the space, the rescue operation fails, and you now have two bodies to recover.
Identifying the toxins that cause those collapses requires knowing the heavy-hitting chemicals frequently tested on the boards. Let's start with crystalline silica.
Silica dust is generated anytime you cut, drill, or crush concrete, brick, or masonry. It shatters into microscopic, jagged, crystalline structures that penetrate deep into the alveolar sacs of the lungs. The body cannot dissolve them, leading to silicosis, an irreversible suffocating scarring of the lung tissue.
OSHA recently drastically lowered the PEL for silica to 50 micrograms per cubic meter of air. But the crucial exam takeaway is understanding Table 1 of the silica standard. OSHA created a specific compliance table listing 18 common construction tasks.
The beauty of Table 1 is that if an employer rigidly follows the exact engineering controls listed for their specific task, for example, using a handheld concrete saw equipped with an integrated water delivery system to suppress the dust, or a masonry drill equipped with a shroud and a HEPA-filtered vacuum, and they adhere to the specified respiratory protection, they are completely exempt from conducting complex, expensive air monitoring.
However, those controls are non-negotiable. Wet methods are mandatory. Dry sweeping of concrete dust is explicitly prohibited under the standard. Next on the list is hydrogen sulfide, or H2S.
H2S is a highly toxic, flammable gas naturally produced by the anaerobic decay of organic matter. It is a massive hazard in municipal sewer operations, pulp and paper mills, and the oil and gas sector. It is a chemical asphyxiant that interferes with the cell's ability to utilize oxygen.
At very low concentrations, H2S has a highly distinct, repulsive odor of rotten eggs. But this presents a terrifying physiological trap: olfactory fatigue. When the concentration exceeds 100 parts per million, the gas rapidly paralyzes the olfactory nerve.
You smell the rotten eggs once, and then the smell completely vanishes. Your brain tricks you into believing the gas is dissipated, when in reality the concentration is rising toward lethal levels.
100 ppm is also the established IDLH threshold, immediately dangerous to life or health. At higher concentrations, approaching 500 to 1,000 ppm, H2S functions as a rapid knockdown gas, causing near instantaneous unconsciousness and paralysis of the respiratory command center in the brain.
Next, cadmium. You will often encounter cadmium exposure during hot work or welding operations, specifically when cutting into older cadmium-plated steel fasteners or structural members, which often look like dull, chalky black metal.
Cadmium is a highly toxic heavy metal. While it causes severe pulmonary irritation, the exams focus heavily on its chronic systemic effect. Cadmium acts as a cumulative cellular poison that specifically targets the renal system, leading to irreversible chronic kidney disease.
Finally, the most infamous occupational hazard in history, asbestos. Its microscopic durable fibers cause mesothelioma, lung cancer, and asbestosis. For the CSP and IH modules, you must memorize the three primary mineralogical forms of asbestos.
We utilize the acronym ACC, amosite, the brown fibers, Chrysotile, the white serpentine fibers which make up the vast majority of commercial asbestos, and chrysotolite, the blue, highly hazardous fibers.
We mentioned the term IDLH earlier regarding H2S. The concept of an atmosphere being immediately dangerous to life or health dictates extreme operational constraints.
An IDLH atmosphere is legally defined as an environment that poses an immediate threat of severe exposure to contaminants, such as radioactive materials, which are likely to have adverse cumulative or delayed effects, or an environment that poses an immediate threat of death. The critical metric you must know is the 30-minute escape parameter.
A worker must be capable of self-evacuating from the environment within 30 minutes without suffering permanent, irreversible harm and without experiencing severe eye or respiratory irritation that would disorient them and prevent their escape.
If a tactical operation absolutely requires entry into a confirmed IDLH atmosphere, the regulations regarding respiratory protection are absolute. Air purifying respirators, no matter how advanced the filter cartridge, are strictly prohibited.
Because APRs do not supply oxygen, and an IDLH environment can rapidly deplete oxygen levels or overwhelm the cartridge's filtration capacity.
You are legally mandated to utilize positive pressure supplied air. This means either a full-size SCBA, where the responder carries a 30 to 60-minute air cylinder on their back, or a supplied air respirator, where the worker is tethered to a remote air compressor via an airline.
But there is a massive caveat for the SAR system in IDLH.
Yes. If using an airline SAR in an IDLH atmosphere, the worker must also wear a 5-minute auxiliary escape cylinder on their hip. If a forklift severs the main airline 100 feet away, that small escape bottle provides just enough breathable air to execute an immediate tactical retreat.
We are entering the final sector of our deep dive, Section 6, Ergonomics and the Human Machine. Ergonomics is frequently dismissed as simply adjusting an office chair, but in heavy industry, it is the science of preventing agonizing, career-ending musculoskeletal disorders. Let's analyze the NIOSH lifting equation.
The NIOSH lifting equation is an advanced biomechanical tool used by safety engineers to calculate the recommended weight limit for a highly specific lifting task. It evaluates the physical stress placed on the L5S1 spinal disc.
The math begins with a foundational baseline known as the load constant. The load constant is exactly 51 pounds.
That 51 pounds represents the absolute maximum weight a healthy average human should lift under completely ideal laboratory-perfect conditions. Ideal conditions mean the object is held perfectly tight against the chest, at exact waist height, with absolutely zero twisting of the torso, and the lift is only performed once.
But the reality of a manufacturing floor or a construction site is never ideal.
Which is why the equation utilizes a series of mathematical multipliers, variables for horizontal distance, vertical distance, asymmetry, and frequency. Every time the real-world task deviates from the ideal, the multiplier reduces that 51-pound limit.
If a worker has to reach out with extended arms to grab a box off a pallet on the floor, the biomechanical leverage against the lumbar spine is massive. The equation's multipliers reflect that stress, dropping the safe recommended weight limit from 51 pounds down to perhaps 18 or 20 pounds.
If the box actually weighs 50 pounds, but the equation dictates the safe limit is 20 pounds, you have a severe ergonomic hazard. You calculate the overall risk using the lifting index. You divide the actual load weight, 50 pounds, by the recommended weight limit, 20 pounds, resulting in a lifting index of 2.5.
The ultimate goal of an ergonomic intervention is to engineer the workspace, perhaps installing a spring-loaded pallet leveler to bring the lifting index back down below a value of 1.0.
Ergonomic hazards also encompass the physical damage caused by power tools. Hand-arm vibration syndrome is a severe, chronic condition. The exams will test your understanding of the physics of vibration, specifically frequency versus amplitude.
Think of a high-speed pneumatic die grinder. It emits a high-pitched whine. That is high frequency. But the physical movement of the tool is tiny low amplitude. While irritating, it is not the most destructive force.
The tools that cause the most severe, rapid neurological and vascular damage are those exhibiting low frequency and high amplitude.
Visualize a heavy gasoline-powered soil tamper or an industrial pneumatic pavement breaker. It is a slow, violent, deep, pounding movement. The physical waves of kinetic force transmitted into the skeletal structure are massive.
That specific high-amplitude vibration physically shatters the microscopic capillaries and damages the peripheral nerves in the hands and fingers. Over time, this results in Raynaud's phenomenon, commonly known as weight finger disease. The blood vessels permanently spasm and restrict flow, turning the fingers chalk-white, cold, and numb, leading to massive loss of dexterity and grip strength.
Finally, we must differentiate between two specific repetitive motion injuries. Carpal tunnel syndrome is the most famous. It is the physical compression of the median nerve as it passes through the narrow, bony tunnel in the wrist. It is typically caused by awkward wrist flexion like typing on a keyboard with dropped wrists or highly repetitive finger manipulation.
The exams often contrast carpal tunnel with de Quervain's tenosynovitis. De Quervain's is an acute inflammation of the tendon sheaths, specifically located on the thumb side of the wrist. We historically saw this in tasks requiring repetitive, highly forceful gripping, like using heavy snips to cut sheet metal. Today, we're seeing a massive surge of de Quervain's linked directly to the excessive repetitive use of the thumbs while typing on smartphones.
Wow. We have officially navigated the entire boot camp. Let's execute a rapid debrief. We established the hierarchy of controls, emphasizing that administrative controls outrank PPE because they addressed the timeline of the hazard earlier.
We built out the complex Boolean logic of a fault tree analysis, utilizing AND and OR gates to mathematically deduce root causes.
We decoded the incident command structure, locking in the span of control at an optimal 5 and highlighting the safety officer's unilateral authority to halt operations.
We dismantled the exam's mathematical red herrings, always dividing the TWA by an 8-hour shift, utilizing only recordable cases for the incident rate, proof testing jacks at 125%, separating free fall from total fall clearance, and matching duck inches to feet for ventilation math.
We navigated the lethal nuances of confined space atmospheric testing and IDLH limits, and we broke down the biomechanics of the IOH lifting equation.
Synthesizing this massive volume of technical data is what elevates a candidate from someone who simply memorized the regulations to a certified professional capable of architecting complex life-saving systems.
Before we close out this intensive session, we always like to leave you with a final provocative thought, something that takes the technical data we just covered and challenges you to apply it philosophically to the future of the industry.
I want to focus your attention on the Board of Certified Safety Professionals Code of Ethics. The very first principle mandates that professionals hold paramount the safety and health of people. Memorizing the TWA formulas and the confined space regulations is simply the technical baseline required to get your foot in the door.
The true challenge of your career will be strategic and ethical. Consider our deep dive into the top of the hierarchy of controls, elimination and engineering. As an industry, our highest objective is to physically eliminate the hazard. Increasingly, we are achieving this by substituting fragile human labor with highly complex automation.
We look at a worker blowing out their lumbar spine lifting 50-pound bags, and we solve the ergonomic crisis by replacing them with an automated, multi-axis robotic arm.
It absolutely eliminates the chronic ergonomic risk. But my challenge to you as a future CSP is to critically analyze the secondary effects. Are we truly eliminating risk, or are we simply trading familiar, manageable risks for new, entirely catastrophic ones?
By introducing that complex robotic cell, we have cured the back pain, but we have introduced highly volatile electrical systems, complex software interfaces, and massive unyielding kinetic energy. If a lockout-tagout procedure fails on that new robot during maintenance, the outcome is no longer a localized muscle strain, it is a fatal crushing injury.
As you walk onto your site tomorrow, I want you to look critically at the brilliant engineering solutions your company has implemented and ask yourself, what new, silent risks are these solutions secretly creating, and are we prepared to manage them? A brilliant, necessary question for the modern safety engineer.
You have the technical tools. You know how to spot the exam traps.
Now go out there, pass the boards, and build a safer world. Keep diving deep.